Okay, in this video, we're going to talk about the set abstract data type. Okay, so when we talk about a set, then what we're talking about is a collection of items. And really, this data type is meant to match the mathematical concept of set that you should have already seen about at some point in your education, and that you likely have a very good intuitive grasp of. Like a set is just a collection of things, a collection of items. It could be anything we wanted it to be. On the slide, I'm showing you some sets with integers. Within a set, those items could be ordered. For example, if I have a set of integers, 1, 2, 4, 5, and 11, then I might order them from smallest to largest. Or a set may be unordered. In this case, 3, 5, 2, 9, 1, they're just all jumbled up together in a data structure. Now, whether they're ordered or unordered actually has a pretty big impact on how we design data structures to support them. And we're going to consider both cases. And what we're primarily going to consider this week is the unordered variant, but we'll just talk a little bit about ordering and during this set of slides. I also want to point out that this is different than the ordering we think about with a list. So when we add things into a list, then the order we insert them is the order we care about. Like if we have a queue or a stack, we're inserting things into that list in a very particular order, and the order that we insert them is the order we care about. Whereas with sets, the order we're talking about is the order with respect to their values, like from smallest to largest. So there are different kinds of orders. And when we're talking about sets, we're only talking about ordering with respect to the value of the data. We're not talking about ordering with respect to when they're inserted in the set. Now we don't care about that at all. They could be inserted first or last, and that's irrelevant. All we care about is either their relative value, or we may not care about order at all. And the order in which we add them into the set is irrelevant. We will just get the way the set represents them internally may be totally independent of the order in which they're put in. Okay, so normally we have three different functions, or at least three functions you support on a set: insert, find, and remove. Insert will add an item into the set. Find will determine if an item is already in the set, and remove will remove an item from a set if it's there. It's worth noting that for these sets that we're talking about now, when we do an insert, we'll only insert the item if the item is not already in the set. Okay, so we are going to enforce a uniqueness property of all the things that are collected in a set. Also, the items that we put in this set, could be simple primitive types, or they could be objects with many fields. But whatever the case, we will need to support these three operations: insert, find, or remove. Okay, so here's an example of some set operations. Let's say that I have a set of integers, and I insert 10. Well, if my set already has 5 and 19, then after inserting 10, my set might be 5, 19, and 10. If I insert 10 again, and my set is 5, 19, and 10, well, then the result is just 5, 19, and 10, because into the set, I can't add 10 a second time. And then if I remove 19, then the 19 that was in the set gets taken out, and now I just have 5 and 10. If I try to remove 1, there is no 1, and so nothing happens. I'm still left with the same set. And if I try to find 5, then I do have a 5 in the set, so the result is that I should return true. And you could even imagine a variant of this interface in which not only do I return true, but I return like a reference to that item in the set if I so chose to do so. Sets are really fundamental. They are used in a lot of algorithms. Like one set of algorithms we're going to see them in later this semester are graph algorithms. When we're analyzing graphs, it's helpful to remember the set of nodes that we've previously visited. So it just happens a lot that algorithms want to collect items to denote some intermediate state, or possibly even to denote the final result of a calculation, like here are the set of things you care about. So being able to support sets and being able to support them efficiently is really important. And so a key goal we have in the design of sets is that we can insert, find, and remove items from a set in constant time, in big O of 1 time. And this is possible, and we can do this. And so we're going to We'll look at one implementation first where it doesn't achieve this, and then we'll look at an implementation that does. And we'll think a bit about those differences. Okay, in summary, a set abstract data type is a fundamental data structure used to solve many problems. Sets hold items in either unordered or ordered form. Again, that's ordering based on their value. And they may hold primitive types like int, char, double, or string, or entire objects. Operations on sets typically include something like insert, find, and remove. And we're going to consider implementations as good as O1 time complexity for these operations.